Hello, everyone. So last time we were looking at the properties of combinations and binomial coefficients. So we defined the permutations and combinations last time. Permutations, combinations. So this one, the notation was P and R. This one, the notation was C and R. So permutation means you want to choose, or R permutation means you want to choose R objects out of N objects. And the order is relevant. So for example, we said, if you want to choose a group of 2 people in a class of, let's say, 15, and let's say the first person wants to be, or is supposed to be, let's say, for example, head TA, and the second person, for example, the secretary, for example. So that if their role are different, so then it's important which one is the first person, which one is the second person. But in combinations, order is not relevant. And for example, let's say if I want to choose 2 people out of 15 people, and both those 2 people are going to be TA, so none of them head TA or anything else, so same role. Then in that case, it doesn't matter which one is the first person, which one is the second person, because in any case, they will be just TA, same role. In that case, we use combinations. And so this one, we saw that the formula is given by n factorial over n minus r factorial. This one, another notation for it was n choose r, and the formula is n factorial over r factorial times n minus r factorial. And we also saw about some properties of combinations or binomial coefficients. So these are also called binomial coefficients. Properties of n choose r numbers, so binomial coefficients. So for example, we saw that x plus y to power n can be written as n choose 0 x to power n plus n choose 1 x to power n minus 1 y, and all the way to n choose n minus 1 x y to power n minus 1, and plus n choose n y to power n. We also saw n choose 0 equals n choose n equals 1. And we also saw n choose 1 equals n choose n minus 1 equals n. We also saw n choose r equals n choose n minus r. So this one, we were trying to prove this. And the algebraic proof was simple. We just used the formula for n choose r to prove this property. Now we said that we are going to do another type of proof called a combinatorial proof. Combinatorial proof for n choose r equals n choose n minus r. So what does combinatorial proof mean? So we said that, we are going to interpret, we have 2 sides, left-hand side and right-hand side. We are going to interpret each side using the number of ways to do some specific task. And then we will show that those 2, left-hand side and right-hand side, must be equal to each other. So in this case, n choose r, which is the left-hand side, what does it represent? It represents the number of ways to choose a set with r elements out of a set with n elements. So let me write it down. So note that n choose r represents the number of ways to choose a set A with R elements from a set S with N elements. Okay, so, but one way to determine a set with R elements, one way to indicate which R elements I want to choose is to indicate which elements I will not choose, which N minus R elements I will not choose. If I tell you which N minus R elements I will not choose, then you will definitely know for sure which R elements I will choose, right? So for example, let's say in our class, let's say we have 15 students and I want to choose a group of 2 people to act as TA, let's say. So of course, one way is that I can tell you which students are going to be, I'm going to choose as TA. So let's say if we have, let's say student 1, 2, 3, all the way to 15. Let's say I want to choose, for example, student 1 and 2, for example. So one way is that I can tell you I'm going to choose student 1 and 2 to act as TA. But another way is that I can tell you that I'm not going to choose student 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. So if you know that I will not choose student 3, 4, 5, all the way to 15, then you will know that, okay, well, this means that I'm going to choose student 1 and 2. Right? So that's one way to determine a set A. So let me write it down this way, that so now a set A with R elements can be uniquely chosen or uniquely determined if we indicate, or if we determine, if we indicate which N minus R elements we will not choose. In other words, if a complement, which is S minus A, is determined, which is a set with N minus R elements, which is a set with N minus R elements, then A will be determined. Then A will be determined. Thus, number of ways to choose a set A with R elements is same as number of ways to choose a set A complement with N minus R elements. And in other words, N choose R is equal to N choose N minus R. N choose N minus R is the number of ways to choose a set with N minus R elements. But like I said, you know, if I know which N minus R elements I will not choose, then I will know which R elements I will choose. So every choice of a set with A with R elements is in correspondence with a choice of a set A complement with n minus r elements, which are the elements that I will not choose. So the number of ways to do these two tasks are the same. So that means n choose r is equal to n choose n minus r. So I interpreted left-hand side as number of ways to do a specific task, right-hand side number of ways to do a specific task. And then I analyze that these two number of ways must be the same. And then I concluded that left-hand side must be equal to right-hand side. So this is called a combinatorial proof for this property. All right. Now let's look at more properties for these binomial coefficients. More properties of binomial coefficients. So sigma n choose k from 0 to n, so this is with sigma notation. Without sigma notation, I can write this one as n choose 0 plus n choose 1 dot 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 and n choose n. So then this is equal to 2 to power n. Proof. So let's see how we can prove this. So sigma n choose k from 0 to n, or is same as this expression here. How can I show this is equal to 2 to power n? So let me start with the right-hand side, which is 2 to power n. 2 to power n, I can write it as 1 plus 1 to power n. Now by binomial expansion, which we mentioned before, we derived it last time, but I recalled you today. Let me call this one star. By star binomial expansion star, I can write this one as n choose 0, 1 to power n plus n choose 1, 1 to power n minus 1 times 1, and plus dot 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 n choose n minus 1, 1 times 1 to power n minus 1, n choose n, 1 to power n. But 1 to any power is 1. So this is equal to n choose 0 plus n choose 1 all the way to n choose n. Okay, so this was another property. Another property is sigma minus 1 to power k times n choose k equals 0, k from 0 to n. So proof of this, let me leave as exercise, but you can probably guess what you need to do. Previous property, we had 2 to power n, we wrote it as 1 plus 1 to power n. So this one is 0, and you can write 0 as 1 plus minus 1, and then the whole to power n, and then again use the binomial expansion. And then you will see that 0 will be equal to the left-hand side. So that's easy to prove. Okay. So corollary of 2, property 2 is that we can say n choose 0 plus n choose 2 plus n choose 4 dot 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 equals n choose 1 plus n choose 3 plus dot dot dot. So how can we prove this property? So we just need to expand what we mentioned in property 2. So corollary, by the way, you know the meaning. Corollary means conclusion, right? So conclusion of property 2 is this property. And how can we prove it? We just need to expand what we mentioned in property 2. So let me say proof by property 2. What can we say? So the first term is minus 1 to power 0, which is 1, times n choose 0. And then the second term, if k is 1, minus 1 to power 1 is minus 1. So minus n choose 1. And then plus the next term will be minus 1 to power 2, which is plus n choose 2, and then minus n choose 3 equals 0. So now if I keep the terms, like the positive terms, basically left-hand side, and take the negative terms to the right-hand side, then they will become positive, and therefore I will have n choose 0 plus n choose 2 plus n choose 4 plus dot 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 equals n choose 1 plus n choose 3 plus dot dot dot. So this was easy to prove. Now let's look at the next property. Property 3. Sigma 2 to power k and choose k equals 3 to power n, and here again k from 0 to n. So again, let me leave the proof as exercise. But again, you can probably guess what you need to do, right? So 3 is 1 plus 2. So 3 to power n, you can write it as 1 plus 2 to power n, and then again, expand it using binomial identity, and then derive the left-hand side. It's easy to do. Next property, it's a very important one. It's called the Pascal's identity. So this says n plus 1 choose k, n plus 1 choose k is equal to n choose k minus 1 plus n choose k. So let me prove this property now. So proof. So we can, I can give you algebraic proof and also combinatorial proof. Algebraic proof is easier because it just involves, just some algebra and some just getting common denominator, etc., which is easy to do. So algebraic proof. So if I start with the right-hand side, so that's n choose k minus 1 plus n choose k. So this is n factorial over k minus 1 factorial times n minus k plus 1 factorial, right? Plus n factorial over k factorial times n minus k factorial. Now I need to get the common denominator. What is the common denominator? Because k factorial means k times k minus 1 factorial, right? And n minus k plus 1 factorial, I can write it as n minus k plus 1 times n minus k factorial. And so you know that the common denominator, see, if you have, for example, the common denominator of, let's say, if you have, for example, c over ab plus, let's say, d over, for example, AE, right? So what is the common denominator? The common denominator will be ABE, right? If you have two fractions of this form, common denominator, or LCM, least common multiple. Least common multiple of these two fraction, these two denominators are n minus k plus 1 factorial, right? N minus k plus 1 factorial times k factorial, right? Because k factorial, we could write it as k times k minus 1 factorial. And we have k minus 1 factorial in the first denominator, and n minus k plus 1 factorial, we could write it as n minus k factorial times n minus k plus 1, and n minus k factorial, we have it in the second denominator. So the common denominator, or the least common multiple, is n minus k plus 1 factorial times k factorial. Then from the for the first fraction, the numerator, I have to multiply it with which factor? N minus k plus 1 factorial are the same. Here I have k factorial, here I have k minus 1 factorial, so I have to multiply this with k, because again, k factorial means k times k minus 1 factorial. And for the second fraction, n factorial must be multiplied by, so k factorial are the common, but here in the second denominator, I have n minus k factorial. Here I have n minus k factorial. Here I have n minus k plus 1 factorial. And that means n minus k plus 1 times n minus k factorial. So I have to multiply the second numerator by n minus k plus 1. And now if I simplify this, what do I get? I'll get n factorial times k plus n factorial times n plus 1 minus n factorial times k divided by n minus k plus 1 factorial times k factorial. Now n factorial times k cancels with n factorial times k, and n factorial times n plus 1 is n plus 1 factorial. So this is n plus 1 factorial divided by k factorial n minus k plus 1 factorial. And then this is n plus 1, choose k. Because n plus 1 choose k is n plus 1 factorial over k factorial times n plus 1 minus k factorial, which is my left-hand side. Okay, that's all. So this is the algebraic proof. Now let's look at combinatorial proof. Combinatorial proof of property above. So let S be a set with n plus 1 elements. So let's say A1, A2, all the way to A n plus 1, which I can write it as A1 union A2 to A n plus 1. Okay, now look at the left-hand side of the properties. N plus 1 choose k. That means number of ways to choose a set with k elements out of a set with n plus 1 elements, which I called it S, right? So I want to choose a set, let's say A, capital A, with k elements from this set S. So now n plus 1 choose k is the number of ways to choose a set A with k elements to choose a set A with k elements out of elements of set S above. Now for each choice of A, each choice of a set A, we have two possibilities. We have two possibilities. So case one, either this first element A1 is in A, or A1 is not in A. See, I look at this set S. I want to choose K elements out of these n plus 1 elements. And I'm going to call that set A with K elements. I'm going to call the set with K elements. I'm going to call it capital A. Now that set capital A with K elements either contains this first element A1 or it does not contain the first element A1. There is no other possibility. First possibility, if the set A contains A1, then other than A1, how many elements do I need to choose to be included in A? Because remember, A was supposed to have K elements in total. Now, if A1 is one of them, then we still need K minus 1, K minus 1 additional elements. So case 1, if A1 belongs to A, so we still need an additional K minus 1 elements from elements of S to include in A. And number of ways to do that. Okay, from elements of basically not S, because A1 is already chosen. So A1 is chosen, right? So I still need, other than A1, I still need K minus 1 elements out of elements of this set. K minus 1 elements out of these elements, and then A1 is also one element. In total, I will have K elements. So K minus 1 elements out of, let me say, this set A2 to AN plus 1 to include in A. To include in A. So number of ways to do so is N choose K. N choose K minus 1. Because this set has N elements, and we are going to choose K minus 1 elements out of these N elements. Number of ways to do that is N choose K minus 1. It seems that the screen is freeze. Let me stop share. Share again. Okay, and case 2, if A1 does not belong to A, then we need to choose K elements out of elements of, A2 to AN plus 1 to include in A. Number of ways to do so is n choose k. Right? Remember, capital A is supposed to have k elements in total. If A1 is not one of them, so then we still have got nothing so far for A. So we still need all the k elements to be chosen, this time from this set, because we're assuming A1 is not in A. So all the k elements must be chosen from A2, A3 to AN plus 1. How many ways do I have to do that? Well, this set has n elements and I want to choose k elements. So number of ways to do that is n choose k. Okay, so thus, as case 1 and case 2 have no intersection, number of ways to choose a set A with k elements out of A1 to AN, which is my S, is given by n choose k plus n choose k minus 1. Okay, remember, so let me summarize this for you. We wanted to prove this property here. Look at the left-hand side, n plus 1 choose k. That means that if I have a set with n plus 1 elements, I call them A1 to AN plus 1, I have to choose k elements out of these elements. Okay, so, and the number of ways to choose a set A with k elements out of these elements is n plus 1 choose k. Now, this set A with k elements, there are two possibilities for it. Either this set A contains A1, the first element in S, or it does not contain A1, the first element in S. So you may wonder, why am I emphasizing on A1? Well, no specific reason. You could say the similar reasoning for picking A2, for example. You could say either A2 is in A or A2 is not in A, and give a similar reasoning, you still get the same answer, right? So I just need to fix one element of S and give an argument based on that. So I picked A1, for example. So either the set A contains A1 or it does not contain A1. If it contains A1, remember capital A, the set capital A is supposed to have k elements. If it contains A1, we still need k minus 1 additional elements from this set. How many ways do I do that? Do I have to do that? K minus 1 elements out of n elements. So I have n choose k minus 1 ways to do that. Second possibility, if A1 is not in A, then I still need all the k elements to be chosen from these elements, because A1 is not there, so I still have got nothing for A. So all the k elements must be chosen from these elements. How many ways do I do that? How many ways do I have to choose a set with k elements out of n elements? N choose k. So that is what we got in case 2. And by principle of inclusion exclusion, case 1, case 2 have no intersection, because if A1 is in A, then A1 is not in A. If A1 is in A, then we cannot have A1 not in A, and conversely. So these two have no intersection. So number of the total number, I have to just simply add the number of cases I got, the number of ways I got in case 1 plus number of ways I got in case 2, which is n choose k plus n choose k minus 1. So that means n plus 1 choose k equals n choose k plus n choose k minus 1. Okay. Now remark, using Pascal's identity above, we can conclude that the binomial coefficients can be computed via a triangle of the following form, called Pascal triangle. Pascal's triangle. So this is the triangle. We have 1 here and 1 here. And then we got again 1 here. And 1 plus 1 is 2. And again 1 here. Now again 1 here. 1 plus 2 is 3. And 1 plus 2 is 3. And then again 1 here. And then again 1 here. 1 plus 3 is 4. And 3 plus 3 is 6. 3 plus 1 is 4. And then again 1 here. And so on. So what is the relation between a Pascal triangle, which gives us the binomial coefficients? Look at, these are the binomial coefficients. For example, this is for power 2, see? X plus y to power 2 is x squared plus 2xy plus y squared. So the coefficients are 1, 2, and 1. 1, 2, and 1. Or for the next one, x plus y to power 3 is x cubed plus 3x squared y, 3xy squared, and y cubed. So the coefficients are 1, 3, 3, 1, and so on. Now, what is the relation between Pascal's triangle and Pascal's identity? Well, here, for example, so this is for x plus y to power 1, right? X plus y to power 1 is x plus y. So these are basically 1 choose 0, and this is 1 choose 1. Now, the coefficients for power 2, what are the coefficients? Well, the first coefficient, of course, is 2 choose 0. And the last one is 2 choose 2. What is the middle one? 2 choose 1. But what is 2 choose 1? 2 choose 1. By Pascal's identity, as PI means Pascal identity, I can write it as 1 choose 0 plus 1 choose 1, which are the two numbers I got here in the row above. Okay, so this row, see, are the coefficients for power 1, then power 2, power 3, and so on. Now for power 2, what are the coefficients? 2 choose 0, 2 choose 1, 2 choose 0, 2 choose 1, and 2 choose 2. 2 choose 0 and 2 choose 2, of course, are 1. 2 choose 1, well, of course, one way to find 2 choose 1 is to use the formula for n choose k, and we'll see that's 2. But the trick here is that let's not do that. Let's not use the formula directly. Instead, let's use Pascal's identity. Pascal identity says what? says 2 choose 1 is 1 choose 0 plus 1 choose 1, which means these two coefficients in the row above. See, because n plus 1 choose k. So 2 choose 1 is 1 choose 1 plus 1 choose 0, right? If my k is 1 and my n is 1, 2 choose 1 is 1 choose 1 plus 1 choose 0. And similar thing happens in the next rows as well. So for example, here, so this is again 3 choose 0, the coefficients for power 3. The first one is 3 choose 0, which is of course 1. Then what is the next one? Next one is 3 choose 1, which I can write it as 2 choose 1 plus 2 choose 0, which means, again, this is by Pascal identity, which means 2 choose 0 and 2 choose 1. So these are the two numbers above, in the row above for 3. So 1 plus 2 is 3. Similarly, you can show that this number must be this number plus this number, which is 3. And the last number again, 1. Again, for the next row, you can do the similar reasoning. Like this number, you can show that this number plus this number, so this is 4. This number here must be this number plus this number, which is 6, and so on. So using Pascal triangle, we can find the binomial coefficients. So you probably have seen Pascal triangle in high school. But now you know the reason why Pascal triangle works and why Pascal triangle can be used to find the binomial coefficients. In other words, why should we add these two numbers in the row above to find this number here? Or why should we add these two numbers in the row above to find this number here? So the reason is because of Pascal identity, that well, this number is supposed to be like the second number in the binomial expansion is 3 choose 1. Because of a binomial expansion, but by Pascal identity, 3 choose 1 can be written as 2 choose 1 plus 2 choose 0, which means the two numbers in the row above. Okay, and then for example, this one is x plus y to power 4 is x4, 4x cubed y. 4x cubed y, 6x squared y squared, 4xy cubed, and y to power 4.